Ever wondered how billions of microchips are made from something as simple as sand? In today's video, we'll uncover the fascinating process of turning sand into microchips, the tiny components that power our modern world. Stick around to see how this miracle happens. Before we dive in, don't forget to like, subscribe, and hit the notification bell for more incredible content. Microchips are undoubtedly one of the most revolutionary inventions of the past 50 years. Since their invention, microchips have transformed the electronics industry, evolving into incredibly powerful electronic brains capable of performing more than 1 billion calculations per second. This drastic evolution has led to the creation of highly efficient and compact devices that are used in nearly every modern piece of technology. Creating these miniature electronic marvels, known as microprocessors, is an incredibly complex process. One that is not only highly technical but also requires an immense amount of precision and innovation. But how exactly are these microprocessors made? To fully understand this, let's dive into the intricate and amazing process of producing billions of microchips inside a state-of-the-art semiconductor factory. The birth of microprocessors. Modern microprocessors contain billions of transistors on a single chip, and they form the backbone of nearly every electronic device we use today. Microprocessors power everything from the smallest household gadgets to the most complex smart cars, and their applications span across industries as diverse as healthcare, telecommunications, entertainment, and automotive technologies. They are essential to the functionality of personal computers, mobile phones, washing machines, gaming consoles, and much more. The story of microprocessors began in 1958 when Jack Kilby, an engineer at Texas Instruments, created the first integrated circuit. His invention contained a single transistor, and it was a game changer. From that early invention, the microchip evolved rapidly, with today's microprocessors using nearly 1 billion transistors. This incredible increase in transistor density has been driven by Moore's law, which states that the number of transistors on a chip doubles approximately every 2 years. As a result, processors have become exponentially faster, more powerful, and more compact. A company that produces semiconductor chips might manufacture up to 70 billion microchips every year. These chip-powered devices are used in everything from everyday household appliances like washing machines to highly sophisticated smart cars. Each chip produced is a true marvel of modern miniature manufacturing. What makes a microprocessor work? A microprocessor works by leveraging circuits that consist of millions of tiny components. These components serve as electronic switches, controlling the flow of electricity and, in doing so, enabling data processing. The more transistors that are packed onto a chip, the faster and more powerful it will be. This explains why manufacturers are constantly working to fit more and more transistors onto microprocessor chips. As technology has evolved, the process of creating microprocessors has become incredibly complex. One of the most important stages of manufacturing involves creating the silicon wafers on which the transistors will be built. These silicon wafers are the foundation of all modern microchips, and their creation is a crucial step in the microprocessor production process. Silicon wafers, the foundation of microchips. The raw material for microchips is silicon, which is derived from quartz sand. Silicon is a semiconductor, which means that it can either conduct or block electrical current depending on how it is treated. This unique property makes silicon an ideal material for supporting the millions of tiny transistors needed to create a microprocessor. The first challenge in manufacturing microchips is to create perfect silicon wafers. These wafers must be flawless because even the smallest imperfections in the silicon can prevent the microprocessor from working properly. Achieving this level of perfection took decades of refinement in the manufacturing process. To create these silicon wafers, manufacturers start with a huge single crystal of silicon that is extracted from a molten mass of purified silicon. The process begins with polycrystalline silicon, which is heated to about 1420 degrees Celsius inside a specially sealed oven. This oven is purged with argon gas to eliminate any air. Once the silicon is melted, it is carefully spun in a crucible to form a single crystal. This crystal weighs approximately 200 kilograms and has a diameter of around 200 millimeters. The crystal is so strong that it can support its weight with just a single thread of 3 millimeters in thickness. Once the crystal is formed, it undergoes various tests using chemicals and X-rays to ensure its purity. Then the crystal is placed into a silicon wafer cutter, cutting the wafers. The silicon crystal is cut into wafers using a specialized heavy-duty cable saw. This saw is capable of using a network of very thin cables that move at incredible speeds to slice through the silicon crystal, creating the thin, round wafers that will serve as the foundation for the microchips. These wafers are incredibly thin, measuring only 2/3 of a millimeter in thickness, and they have a purity of 99.9%. While the initial cutting process creates the rough form of the wafers, the surface of the silicon is not yet smooth enough to proceed with further steps. The wafer is polished through a process called lapping, but even after undergoing this polishing step, the surface still has microscopic marks. So, a second round of polishing is done using a chemical process to create wafers with a surface roughness of less than 0.1 nanometers. Once polished to perfection, the silicon wafers are ready for the next phase of manufacturing, the circuit design and chip production. Creating the intricate design for the circuits that will eventually become the microprocessor is a highly sophisticated step that is performed using computer-aided design (CAD) software. Engineers carefully create a detailed blueprint for the circuits that will be etched onto the silicon wafers. Once the design is completed, a thorough verification process is conducted to ensure that the design meets all required specifications. This is a crucial step to avoid any mistakes, as any error at this stage could result in faulty microchips. After this verification process, the wafers are packed into sealed containers and sent off to undergo the next stages of production. The wafers will now be subjected to a long series of steps in which millions of transistors will be placed on the surface. The process of creating these tiny transistors on the wafers is highly precise and requires the use of some of the most advanced technology available. Photolithography, etching transistors onto the wafer. The next critical step in the process is photolithography, where the tiny transistors are etched onto the silicon wafers. This is done using a machine that can print billions of transistors on the wafer every hour. Before entering the photolithography machine, each silicon wafer is coated with a liquid known as the photoresist. The photoresist reacts to light in a way similar to photographic film. The room where this process occurs is kept under yellow lighting to prevent exposure to normal daylight, which could spoil the photoresist. In the photolithography machine, a laser is used to project the circuit patterns onto the silicon wafer. This process works similarly to how images are projected onto photographic film, leaving an imprint of the transistor design on the wafer. Once the photoresist is removed, the design remains on the surface of the wafer, just like a photographic image. However, creating a complete microprocessor requires building the transistors layer by layer. The photolithography process is repeated multiple times, typically anywhere from 15 to 40 cycles, to build up the transistors and other components necessary to complete the circuit. As a result, the transistors are constructed in layers much like building a skyscraper, and these layers eventually form the complex network of components that make up the microprocessor. Enhancing the laser process. As the demand for smaller and more powerful microchips has grown, engineers have faced the challenge of continually increasing the density of transistors on a single chip. To meet this challenge, they have developed innovative techniques to improve the laser technology used in the photolithography process. One key discovery was that by passing the laser beam through a layer of water, similar to how sunlight passes through a magnifying glass, they can significantly increase the intensity of the laser beam. This allows for even smaller and more precise transistors to be etched onto the wafer. The result is transistors that are about 5 times smaller than the smallest bacteria, pushing the limits of what is physically possible in chip manufacturing. Clean rooms and precision manufacturing. Microchip manufacturing operates at an extremely small scale, with transistors measuring just 1/1000th of a millimeter. At such small scales, even the smallest particle of dust can cause a short circuit or destroy a chip. To mitigate this risk, microchip manufacturers operate in extremely clean environments. Before entering the manufacturing area, workers must don protective suits designed to prevent contaminants from entering the clean room. The air inside the factory is constantly filtered and refreshed, with the entire room being refreshed every 2 minutes to maintain an environment that is 10,000 times cleaner than the air outside. The clean room itself is approximately 18,000 square meters in size and relies on 12,000 tons of air conditioning equipment to keep the environment as clean as possible. This is necessary to ensure that the delicate process of making microchips is not compromised by airborne particles. Copper interconnections. After the transistors are etched onto the silicon wafers, the next crucial step is to establish connections between them using ultra-thin interconnecting wires. These wires, typically made of copper, are essential for forming the integrated circuits that enable the microprocessor to function. However, before applying copper, a barrier layer is first deposited onto the wafer. This barrier layer serves to prevent unwanted short circuits between the copper wires and the surrounding silicon, thus ensuring the reliability and performance of the final chip. Once the barrier layer is in place, the wafer undergoes a process known as trenching, where small grooves or trenches are etched into its surface. These trenches are carefully designed to create the necessary space where the copper interconnections will be laid. The depth and width of these trenches are critical because they determine how well the copper will fit and whether the interconnections will be made with the required precision. With the trenches prepared, the next step is to fill them with copper. This is done through a process called electroplating, where copper is deposited into the trenches through an electric current. The copper fills the grooves, forming the interconnecting wires that will link the transistors together. After the copper has been deposited, the wafer is polished to remove any excess material. The excess copper is ground down to the edges of the trenches, leaving only the copper interconnections intact. This meticulous process ensures that the copper wires are precisely isolated from each other, preventing any electrical interference. The result is a highly functional integrated circuit, with each transistor properly connected and ready to perform its specific role within the microprocessor. The final stages: testing and packaging. The next step is testing to ensure each chip meets the required specifications. At this stage, the chips are thoroughly tested for performance, reliability, and functionality. Manufacturers utilize specialized testing equipment that allows them to check hundreds or even thousands of chips simultaneously. This equipment evaluates whether the chips can perform their intended functions without errors, ensuring they meet the precise standards set for modern microprocessors. During the testing phase, electrical and functional tests are conducted to assess the behavior of the transistors, the connectivity between them, and the overall performance of the integrated circuits. This process helps detect any defects, inconsistencies, or malfunctions that may have occurred during the manufacturing process. Chips that pass these tests are deemed ready for the next phase, while those that fail are either reworked or discarded. After passing the rigorous testing phase, the functional chips are carefully separated from the silicon wafer. The chips are then prepared for packaging, the final step of the manufacturing process. Packaging plays a crucial role in protecting the delicate microchips from physical damage, contamination, and electrostatic discharge. In conclusion, the process of transforming sand into billions of microchips is a remarkable feat of modern engineering and innovation. These chips, containing billions of tiny transistors, are then interconnected, tested, and packaged for use in a wide array of electronic devices. The journey from sand to microchip requires cutting-edge technology, a glimpse into the extraordinary journey from sand to microchip. It's fascinating how such a simple material can be transformed into the powerful heart of the devices we use every day. The complexity and precision involved in making these tiny yet mighty components is truly awe-inspiring. If you enjoyed this deep dive into the world of microchips, make sure to hit that like button, share this with someone curious about technology, and subscribe for more amazing insights. Stay tuned for more mind-blowing content, and thanks for watching.